Here is another very important property of random walks in expander graphs. So suppose we have a constant degree expander graph and that there is some subset of vertices that we are interested in. So let's call it A. Now consider the process of generating a random walk in the graph starting from a random vertex. So we pick some vertex v1 uniformly at random from V, and then we pick some vertex v uniformly at random from the neighbors of v1. Then we pick some vertex v3 uniformly at random from the neighbors of v2, all the way to some vertex vk that is chosen uniformly at random from the neighbors of vk minus 1. Now we may ask how often this random walk starting from the first vertex and continuing for a while will hit the set A. So we might be looking at the cardinality of the intersection between A and the number of the vertices generated by the random walk. So this is a random variable whose sample space is the set of random walks in the graph. Well, the expected number of times that we hit A will be k times the density of A. And it turns out that the difference between the actual number of times that we hit A compared with this expectation, it's usually not very large. So the probability that this difference is more than epsilon times k is exponentially small in k, where the constant in this big omega notation will depend on the expansion of the graph. But if the graph is an expander of constant expansion, this will be a fixed constant. Notice the similarity between this bound and the Chernoff bound. The reason why this bound is very useful is that often randomness is used in probabilistic algorithms to generate elements of some unknown set, maybe from a set that is known, but from which it's hard to construct elements. And so then in the algorithm, we specify a step where several random elements of some finite set are generated uniformly and independently. But really all that we need from those elements is that they satisfy a Chernoff bound pretty much of this form. So in such cases, instead of generating elements uniformly and independently at random, it's possible to generate them through a random walk in an expander. And the difference in the amount of randomness that is needed can be significant, because if we want to generate k elements out of a set of size n uniformly and independently at random, then we're going to need to use k times log n random bits. But if we want to generate k elements from a set of size n through a process of this form, then we do need log n bits to generate the first element, but then for every other element we just need the constant number of bits. So the number of random bits that we need in total is only order of k plus log n. And when k and log n are approximately the same, this is log n squared and this is order of log n, so this can be a fairly significant saving. So because of properties like this and others that we will study in the second part of the course, constructions of expanders are very useful, but they're also very difficult. Some constructions are not very difficult to describe, but they're extremely difficult to analyze. And some others that we will see in some detail are a bit complicated to describe, although not very hard to analyze. So let me show you an example of a construction that is very easy to describe, but whose analysis is extremely hard and completely beyond the scope of this course. So this is a three-regular graph, or actually a family of three regular graphs, of which this is an instantiation. So whenever P is prime, we can get a construction where the set of vertices are the integers mod P. And the edges of this graph are all the edges of the form I connected to I plus 1 mod P. This is an undirected graph, so we also have the edge connecting I with I minus 1 mod p, hence the cycle. And then we have the edge for every I different from 0, from I to I inverse mod p. So every vertex is connected to its multiplicative inverse modulo p. And so this is a tree-regular graph, with the only exception that the vertex 0 does not have this extra edge. The vertex 1 has this edge, but it's a self-loop, but except for this couple of exceptions, every other vertex has 3 neighbors. And the graph could be patched to make it tree-regular if we insist. And it can be proved with an extremely difficult argument that there is an absolute constant such that for every arbitrarily large prime p, if you construct a p-vertex graph according to this definition, this tree-regular graph with p vertices will be an expander whose expansion is at least this absolute constant. Since the definition is so simple, it seems that there should be an elementary proof that this family of graphs are expanders, and this would be a very interesting result. But so far, the only known proof uses fairly advanced material from number theory. In the third part of the course, we will analyze the convergence time of random walks in general graphs. As we said, if we have a graph of constant expansion, then a random walk in G will converge to the uniform distribution of vertices of the graph in time logarithmic in the number of vertices. From results in spectral graph theory that we will talk about next week, and from some connection between spectral graph theory and random walks, it's possible to prove that in general, if one starts from an arbitrary vertex and then takes a random walk in a regular graph, then it only takes at most order of 1 over the square of the expansion of the graph times log of the number of vertices, number of steps, until one reaches a point where the distribution of the current location of the random walk is uniformly distributed among the vertices. So when the expansion is a constant, this 1 over expansion square is also a constant. So the total bound is logarithmic. It turns out that the time that it takes for a random walk to get to a uniform vertex is also at least 1 over the expansion. So if instead of asking exactly how many steps does it take for the random walk to converge to the uniform distribution in the graph, we're asking, is it true that polylog n number of steps are sufficient? Well, then the answer is yes, if and only if the expansion of the graph is at least 1 over polylog n. So at this level of precision, the convergence time of the random walk is captured by the expansion of the graph. So why are we interested in whether or not a random walk in a graph converges, let's say, in 1 over polylog n number of steps? Well, let's give a concrete example and then see what is the general paradigm that this example comes from. So let's say that we are given an undirected graph G, and that we are interested in the problem of generating uniformly at random a matching in this graph. So a matching is a collection of edges of the graph whose endpoints are pairwise disjoint. So here is a possible approach to this problem. So our algorithm will work as follows. It starts by creating some arbitrary matching. This could even be the empty set. And then it repeats the following loop several times. It finds an augmenting path, or actually it could be any path, and then it computes the symmetric difference of the edges in a path and the edges in M. This path could be a cycle, and this path is chosen randomly in a certain way. So the algorithm starts from a fixed matching, say the empty set, and then repeatedly it updates it according to some probabilistic rule. Now we would like to say that if this probabilistic update is performed sufficiently many times, then the matching that the algorithm constructs contains enough randomness that it is in fact uniformly distributed among all possible matchings. But how could we make a claim of this type? Well, then what we will do is to construct an auxiliary graph. This graph will exist only in the analysis. It will not be part of the algorithm. Let's call this new graph H. So this graph will be a graph that contains one vertex for every possible state of the algorithm. So it will contain one vertex for each matching of the graph G. And then it will contain one edge for every possible transition of the algorithm. So if this is a matching M in G and this is some other matching M prime in G, this edge exists in H if one of the possible one-step transitions of this algorithm is to start from M, then find some path P, and then construct M prime as the symmetric difference of M and the path. So this means that we can think of what the algorithm is doing as starting from the matching corresponding to the empty set, and then performing a random walk in this graph of length equal to whichever is the number of steps after which we stop the algorithm. So something that follows from the theory of random walks that we will study is that if we have some graph that is regular and that is undirected and that's connected and not bipartite, then no matter where we start in the graph, if we perform a sufficiently long random walk, we will end up at a place that is uniformly distributed, at least approximately uniformly distributed, among the vertices of the graph. And we can set up the random choice of the path so that this graph will be in fact undirected, connected, and regular. So that it's true that after a sufficiently large number of steps, the algorithm will converge to an internal state, which is a random matching of the original graph G. But how long is this sufficiently long random walk that will get us to a uniformly distributed vertex? In general, this could be polynomial in the number of vertices of the graph, which would be exponential in the number of vertices of G, possibly, because G might have an exponential number of matchings, and every matching of G is a vertex in H. However, we also know that if the expansion of H is large, then the convergence time of the random walk in H is not very large. In particular, the convergence time of a random walk in H, which will be the convergence time of this algorithm, is bounded by 1 over the square of the expansion of H times log of the number of vertices of H, which is at most the number of vertices of G factorial. So n is the number of vertices of G. So if the expansion of H is inverse polynomial in the number of vertices of G, then this is a polynomial time algorithm that finds a uniformly random matching in a graph G, because log of n factorial is about n log n. Turns out that if we choose in the right way the random path in this iteration, then we can prove that the expansion of H is in fact inverse polynomial in n, and so that this whole algorithm converges quickly. So, but why would we want to find a uniformly random matching in a graph anyway? Well, the reason is that this algorithm for finding random matchings will be simple instantiation of a very general approach to sample elements from very complicated distributions. And this method will also apply to distributions that are not uniform, but that are weighted. Possibly they are weighted so that if the set that you are sampling from are the solutions to some optimization problem, then optimal and near optimal solutions will have higher probability in the distribution. So that if we can sample from such a distribution, we will tend to generate optimal or near optimal solutions. And the Metropolis algorithm is a generic application of this principle, and it works very well in practice. So what we will see is a few of the techniques that one can use to generate these algorithms, which are called Markov chain Monte Carlo algorithms. And one technique will be based, as in this case, in bounding the expansion of this auxiliary graph that represents the states of the algorithm. Another technique will be called coupling, and it will be conceptually quite different.